in response to Hyogo's question at the end of last time, where he asked, in what sense do we get an elliptic PDE, because this differential inclusion we're talking about seems to have nothing to do with ellipticity, as you might see it from your standard PDE textbook or course. And indeed, that's the case. But it does, these things do connect. And in showing that, I'm going to be able to present a nice little theorem as well. So this is the theorem we're going to talk about today. So theorem. Suppose K. So we're going to do this in n by n, but there's absolutely no difficulty in doing this by m. I just don't want to deal with m and make potential typos. So we're just doing n by n, and as a subspace, or maybe I just write n by m and then do the special case in the proof, because it'll state the theorem in full general. With no rank 1 connections. Then the differential inclusion U belongs to L almost everywhere for U belong to W1, 2. Improves regularity, gives that U is C infinity. Okay, so we saw this in the special case of the conformal matrices, right? That's one of our early differential. L is K. L is K. So I called our sets K throughout. So we've got some K inside m by n. It's a subspace with no rank 1 connections. Then the differential inclusion gradient belongs to K almost everywhere for any sublove function gives that U is C infinity. And let's make our life simpler, and let's just deal with it defined on the entire domain like this. Okay, so we have seen the special case. Of K being the conformal matrices. This is a subspace without rank 1 connections in 2 dimensions. But now we claim that this is true for any subspace without rank 1 connections. And this is how it is going to work. So, given. So this is actually going to be the coordinates of a mapping from n by n to n by n. But let's just write them like this. We're going to write ij alpha beta for ij alpha beta 1 up to n. Given this collection of coefficients, we say it's elliptic if and only if the following is true, that if we take the sum ij alpha beta equals 1 up to n of ai aj beta alpha aij alpha beta. This thing has got to be bigger than some lambda of a squared b squared, like this, for any a b belongs to Rn. Okay, this is the standard definition of ellipticity when we have a system of PDE, and I'm going to try and explain why this is the natural definition. and it goes like this. So what this thing is doing is that it is charging rank 1 matrices. It is not allowing us to create a bilinear form out of rank 1 matrices that collapses them. And let me try and explain why. So from PDE, we often consider bilinear forms like this. This is often the start of existence proofs for linear PDE. To consider a bilinear form, we apply Lax-Milgram, but we need this coercivity of Lax-Milgram. So consider this bilinear form B of U V, which is defined like this. The sum I, J, alpha, beta equals 1 up to n of an elliptic collection of coefficients where we write like this. We have ui comma alpha vj comma beta. Okay, so claim, and we're going to need this later for our proof of this statement as well, that we have b of u is bigger than lambda times u squared for some lambda, or for this lambda actually. And this is one of the key hypotheses needed for Lax-Milgram, and it's also going to be useful for us going forward. Okay, so why does this follow? I forgot to integrate this, so that's where we are integrating. And we're integrating in Rn, but I'm not going to write double integral, obviously, because now we're in Rn. So you have to remember that this is not a line, this is not integral in the real numbers, this is an integral in Rn, okay? Because u and v are mappings from Rn to Rn. Yeah? So we have these indices, we have u has got coordinates u1 up to un, and we have partials alpha from 1 up to n as well. Yeah? Everybody with me? Thumbs up if so. Okay, cool. So why is this the case? Well, let's do this calculation. So if we write like this, b of u v, these are constant coefficients, right? These are just numbers, so we can just take this stuff outside. And then we're going to have ai alpha, and then the integral of ui alpha vj beta dx. And then we're going to apply Plancherel's theorem to this thing right here. Okay, so now we've got the integral in dx. We're going to apply Plancherel, and we'll have the integral in the frequency variable psi. Okay, and psi will be over Cn complex numbers to the power n. Okay, so then this will be so this is the Fourier transform of the ith coordinate with the alpha's partial, so I'll make sure that the hat goes clearly over this partial like this. And now we're going to have Fourier transform of vj comma beta, Fourier transform. And now the integration with respect to psi, which is the frequency variable. Yeah? And recall that so this is back when we talked about the background for Korn's inequality, we went through this stuff. What happens when you take the Fourier transform of a vector value function. So if we take the Fourier transform of the gradient of a vector valued function, so it's a function of the frequency phi, this we saw turns out to be 2 pi I of u, the Fourier transform of u itself, tensor product with psi, like this. So if you don't remember this, go back and look at that video. This is what we worked out. Okay? And the key point was that this thing was a rank 1 matrix, right? We take the Fourier transform of the gradient, and it turns out it gives us a rank 1 matrix. Okay? And so what does that mean? So this thing is the Fourier transform of the I alpha coordinate of this thing, right? The I alpha coordinate. So let's write it like this. So Ui alpha Fourier transform. That's the same as the I alpha Fourier coordinate of this matrix. So let's write it like this. Du. Okay, so let's include the psi since it's on that side. Transform this is the same as the Fourier transform of the entire matrix, but we take the I alpha entry of this matrix and the I alpha entry of this matrix. So we have a problem because we have two i's. So we're going to have to remember that an I, which is a subscript, is a parameter running from 1 to n, and the I, which is appearing as a multiple of something, is the complex number I. Sorry about that, but let's just deal with it. So we have this guy. It's the ith alpha, so it's going to be the ith row, the alpha's column. So that's going to be the same as 2 pi I, and then the ith row of this guy, which is just the Fourier transform of the ith coordinate, evaluated at psi, like this, and times the alpha of this guy, like this, just directly from this thing. Okay. So we can put that into this expression here, so call that thing star. So from star, we get that Bu of v is equal to the sum I j alpha beta equals 1 up to n aij alpha beta. And then the integral, and now we're going to put our expressions for what these things are. So this is going to be 2 pi I of psi times psi of alpha. And then there's going to be another 2 pi I, so that'll kill the this thing. So we'll have like squared and a minus sign here, like this. And then we're going to have v j Fourier transform at beta, like this, and oops, d psi. Okay, and then I can put the summation inside this thing again. This is just a constant we're going to pull outside. So then this is going to be, I'm running out of space, minus 2 pi squared of integral of the sum I j alpha beta 1 up to n of these coefficients a alpha beta I j, and then these things. So I'm not going to write, or I'll have to write actually, u hat I v hat j times psi alpha and psi beta, like this. D psi. Integral in Rn. Okay? All right, so that makes us happy, because if we look at this expression here, then if we were to take u to be equal to v, or the other way around, v equals u, which is the same thing, then this a could be this vector a could be the Fourier transform of u tilde, and then this vector b could be the vector psi. We'd have exactly that that from this lower bound here, I'm going to erase some space because we need these things. So let's call this thing star star. So from star star, we will have that B of u is equal to this minus 2 pi squared, and then this expression like this, where we have the, well, I can write the whole thing out, perhaps, maybe that's easier. So we have the integral of sum I j alpha beta equals 1 up to n of aij alpha beta, and then u hat I of the u hat j of zeta times zeta to the coordinate, zeta, the bth coordinate, and then the alpha coordinate, and then integrated, right? And then we take A to be this guy here, and we take B to be this guy here, and we're directly in a position to apply this lower bound right here onto this thing, right? So then B of u is bigger than equal to, well, let's put the absolute value like this. So the minus sign shouldn't be here, and I'm wondering, about that, or if it's important at all. Okay, I don't think it's important. So the absolute value of this thing is bigger than 2 pi squared, and then by this inequality, the integral of lambda of tilde like this squared phi squared d phi like this. Does everybody agree? Yeah. And this thing itself is just the norm of this matrix right here, or almost the norm, right? Because this thing is a rank 1 matrix, so its Hilbert-Smith norm is just this guy squared times this guy squared, square rooted, with whatever the absolute value of this thing. Yeah? So, running out of space still, let me erase some more. Let's call this thing star star star. And from star star star, we have that the u hat of psi squared is equal to 2 pi squared times u hat psi squared, right? Yeah? Everybody happy? Yeah? So this thing means that E of u, absolute value, is bigger than, we can absorb actually the 2 pi, so it's bigger than lambda, the integral of this thing, Fourier transform of this guy, squared dx, and then by Plancherel again, this is the same as lambda times the integral. Now we just write this in the Euclidean variable like this. Oh, this is d psi and this is dx. And that's the coercivity inequality that we claimed. We wrote total nonsense that we wanted to claim. Lambda u squared dx, like this. Okay. Cool. So ellipticity allows us to to get this lower bound, or get this estimate required for the Lax-Milgram, and also this is the kind of key estimate, as we'll see, needed to do these kind of Cauchy-Pauli inequalities when we have constant coefficient elliptic systems. We're going to see that fall out. All right. Everybody happy before I erase the board? Yeah? Somewhat technical stuff, but it's just linear algebra and Fourier transforms, basically. Yeah? Cool. All right. Let's keep going. So, I claim that this condition is somewhat natural because we can show this estimate. And now we're going to see how that connects to subspaces without rank-1 connections. Suppose K is a subspace with no R1 connections. So it's elliptic in the sense of Sverak, because every tangent space of this subspace is the subspace itself, and it has no rank-1 connection. So this is an elliptic. I mean, that's why I guess he gave his definition elliptic. So I just break out a new pen. So there we go. Is elliptic in the sense of Sverak. All right, and let's do the following thing. So let A from m by n going into n by n be, well, actually do it this way. Let A from n by n be the projection into the orthogonal complement of K. Okay. And let P m by n be the projection onto K itself. Okay, so first claim that if we take A of any rank-1 matrix like this, it's bigger than lambda, or it might not be the same lambda, but let's choose a different one. Let's call it mu of the absolute value of A cross product B for some mu. Okay, why so? So for any rank-1 matrix, it's equal to the sum of its projections onto into these orthogonal subspaces K and K orthog. So it's equal to A plus P of A cross product A, like this, right? That's definitely the case. And if we had that this thing was equal to 0, then we would just have that this guy is its projection onto K itself, but K has no rank connections. So I should put this here, belong to K. But K has no one. There's no R1 connections. So that would imply that A cross product A has to equal 0 itself. Yeah? Because the only way we can have a rank-1 matrix inside K, which has no rank-1 matrix, is if this guy is equal to 0. Yeah? So if we have a non-zero A rank-1 matrix A cross B, then we cannot have this. Cannot have this. Yeah? Yeah? Everybody with me? Thumbs up if so. If A cross B is not equal to 0, then A cross B is not equal to 0. Thumbs up if you agree. Yeah. Okay. So let's take a non-zero A cross B. Yeah. So a non-zero rank 1 matrix. Yeah? Suppose we take the projection onto the orthogonal complement of K and it's equal to 0. Yeah? Well, we have that A cross B is the unique decomposition into projection onto the subspace K perp and onto K. And if this part's equal to 0, then it must be entirely projected onto K. In other words, it's equal to its projection onto K. Yeah? And therefore, this guy is inside the subspace K, so it cannot be a rank 1 matrix and be non-zero inside this subspace. So it has to be equal to 0, which is a contradiction. So for any non-zero rank 1 matrix, the projection onto the complement is of K, into the orthogonal complement of K is non-zero. Cool. Okay. So this is a homogeneous kind of situation. So consider the following thing. So the infimum of this thing has to be bigger than 0, since if it wasn't, by compactness we could get a contradiction. Yeah. So this is strictly bigger than something, and let's actually give it some name. So this infimum, let's call this infimum mu. Right? You agree that by compactness this is a closed set, because having rank 1 is a closed condition. Yeah. So we must have this. But then if we do this, like this, so the norm of this matrix has got norm 1. So in 2 by 2 this is easy to see, but it's just generally true. So this thing is bigger than, well, it's bigger than equal to mu, but this is a homogeneous condition, so we can just, I mean, this is a projection, it's a linear mapping, so this implies that, well, this implies our estimate. Everybody agree? Yeah, thumbs up if you agree. Good. So this is how we're going to use this. So notation. So let E alpha I belonging to the n by n matrices be the matrix with 1 at the ith row alpha's column entry and 0 elsewhere. Right, so this thing, as we run I from 1 to n and alpha from 1 to n, this will form a basis from the space of matrices. Yeah? We can use this basis to actually give ourselves coordinates or coefficients of this projection. So define A ij alpha beta belong to R by A acting on this guy, alpha I, is the sum from j and beta equals 1 up to n of a I j alpha beta of e j beta, like this. Yeah? That thing defines our linear mapping. Yeah? So these coefficients are what we need. So we claim the following thing, that if we take A cross product B dot product A cross product B, like this thing, then this thing is going to be equal to A squared B squared, or big and equal to mu A squared B squared. And that thing I'm going to show is equivalent to ellipticity of our coefficients. Yeah? Like this, okay? This is what we claim. And how are we going to see this? So, to see this, note the following, that we can write A cross product A this is the same as the projection onto the orthogonal complement of K plus the projection onto K of this guy, like this. Yeah. But again, this is a rank 1 matrix, so when you project it onto something which has no rank 1 matrices, then the projection is 0. Okay, so this part just vanishes. So then this thing is just the same as A, like this. And then this thing, just from this, we see is bigger than, oops, not from this, but from previous estimate, this claim here. Just from this thing, we see that this thing is bigger than mu squared, A squared, B squared, because this is just the Hilbert-Smith norm of this guy squared, right? So it just follows directly from this. So our claim is established. All right, so with this notation and with this inequality we've just shown, I'm going to show that this is the same as having ellipticity in the sense we started with on the next board. Okay, so what we've seen is that A cross product B, when we do the matrix dot product with A acting on this guy, this is bigger than mu squared, A squared, B squared. Yeah? So if we look at this guy, A cross product B, then in our matrix notation, that's the sum from I alpha equals 1 up to n of AI beta alpha of EI alpha. Yeah, because in this cross product, the ith jth entry is given by AI bj, or let me say the I alpha entry is given by AI b alpha. So it's this. Yeah. Where recall this guy is just a matrix whose ith row and jth column is 1, and everything else is 0. Everybody agree? Thumbs up if you agree. Maybe you're frozen. Yogo, do you agree? Ah, so maybe he's just frozen. Okay. Well, I can choose my index as I want. So this is a matrix in MIN. Oh, I see what you. So the conventions of this thing is that it's easier to deal with I and alpha and j and beta rather than I and j for reasons that fall out later. So, but you can take alpha to be j, and then it's the. Okay, cool. So let's look at what A acting on little a cross product B is in our notation. So then this is the sum I alpha equals 1 up to n of AI beta alpha of A acting on this guy like this. Yeah. And therefore, in our notation, then this thing is the same as A alpha. This thing, and here we're going to have Aij. I got to do the summation. The sum of j beta equals 1 up to n of Aij alpha beta of Ej beta, just using what these Aij alpha beta are defined to be. Yeah? So putting that expression together, then this is the sum Ij alpha beta equals 1 up to n of Ai beta alpha, Aij alpha beta of Ej beta. Yeah? Cool. So what does that mean? That means that the j beta entry of this matrix is given by the sum over I alpha of this expression. Yeah? Yeah? Cool. So when we do this tensor product like this, or when we do this matrix dot products like this, then we have that A cross product B it is the sum of so let's do this like one step at a time. So it's the sum j beta equals 1 up to n of Aj beta B times the Bj entry of this guy. Or JB entry of this guy, right? And the JB entry of this guy is, again, the sum of I alpha from 1 to n of this expression like this. Yeah? So putting all that stuff together, then we are actually going to have the sum j b I alpha 1 up to n of Aj b beta Ai b alpha of Aij alpha beta times nothing. That's it. That's it. That's our expression. Yeah. And we've seen that this thing is bigger than or equal to mu squared of A squared B squared, and that's exactly ellipticity in the sense that we defined it before. Yeah. So the coefficients that define this projection onto the orthogonal complement of the rank 1 subspace form an elliptic system. Yeah? Cool. All right, so how does this help us get regularity? So let me write this down. So I said I, j alpha beta, j alpha beta belonging to 1 up to n form an elliptic system. Or are elliptic in the sense before. Are elliptic in the classical sense. Classical PDE sense. Okay, so, cool. So we've learned that if A is the projection of orthogonal projection onto subspace K, which has no rank-1 connections. Then we have that A satisfies this inequality. Which is exactly the classical ellipticity condition that we discussed before. So if we have that Aij alpha beta are defined by A of E I alpha is the sum of J beta equals 1 to N A I J alpha beta of E beta J. So these are the coefficients that define this projection, as we've talked about before. Then this thing is exactly the ellipticity condition on these coefficients, right? So we're going to use the very first estimate we achieved for this, for a set of coefficients that actually satisfy this. So then take some, say W belongs to W1, 2 of N, and note. So I mean, this is just writing out the thing which we did at the very first, the very beginning of this video. Then note the following: that the integral of A of du, dw dot product dw dx. What is this? Well, we are going to expand out what this is. So this is the sum alpha equals 1 to N of this guy I alpha times W I comma alpha, like this. And then what is this guy? This is integral of the sum I alpha equals 1 to N, the sum J beta equals 1 to N of A I J alpha beta of W J comma beta W I comma alpha dx, like this, just using this expansion and applying it to this guy right here, right? Cool. And then this is the thing that we saw we can bound by this. Okay, and that was our first inequality. That was the thing that we did with the Fourier transform and Plancherel's theorem. So Now we're going to apply this for the differential inclusion into our set K. So suppose U belongs to W12, Rn into Rn, and the U belongs to K almost everywhere. Then take a test function. Say rho of complex support in Rn, and let us do the following. Let's consider this integral. The integral of A, the gradient of U times rho, dot product, the gradient of this thing, like this. Okay. So by the inequality we've just talked about, this thing is greater than or equal to the integral of the gradient of U times rho, like this, squared dx with some constant. Should I put a constant here? And what else do we know? We know that d of U rho is gradient of U times rho plus U cross product gradient of rho, like this, right? And so when we do A of this thing, then that's the same as A applied to this, but gradient of U is inside this subspace A, subspace K, and A is the projection onto the orthogonal complement of K. Therefore, A acting on this will just be 0. So this thing is just A of U cross product gradient of U, gradient of rho, like this. Yeah. Cool. So putting this into star, then what do we have? We have the integral of A of U cross product gradient of rho, the product, and then let's break this guy up into its bits. U of rho plus U cross product rho, like this, is bigger than or equal to C, integral of this thing. And this guy too, we want to break up. And this will be the U of rho plus U cross product gradient of rho squared dx, like this. Right? And then this thing we can expand out like this. So this will be gradient of U squared rho squared. And then this mixed term, I need two of these, the U of rho. And then this term. Okay. And we are going to put these guys onto this side because what we have going on here is either a product of U and U or a product with U and rho, right? Which will ultimately allow us to control this thing by something which we're going to estimate by Cauchy-Schwarz inequality. It's either going to be a product of U and U from here, and that's underline the guys we don't have to worry too much about. It's going to be this stuff, it's going to be this stuff, and then we'll have the mixed terms, which will be this and this, and those are the guys we'll use Cauchy-Schwarz with. So there's some cleanup required to put the stuff we don't want on the left-hand side, and on the right-hand side we're just going to have this thing, and so let me write it like this. We're going to have du, this thing squared, dx is less than constant, and then we'll have all these various bits, right? We will have this thing, okay, okay, from this we will have our friend here, which is a very similar term to this. So rather than write it again, this thing for sure is it's a linear projection. So this thing for sure we can just bound by a constant. Well, in this case, no constant required. We can bound it by this, and then we can absorb this term. No, that's good. Say that again. So that one is backtrack, back left, right. So this thing is the same as this thing ultimately, right? So then we can just replace this by this guy squared, yeah, which will take care of this and this. And in the mixed terms, we'll have this times this and this times this. Now again, A is a projection, so we can bound the absolute value of this thing just by what's inside it. So that'll ultimately mean that we can have here, and then this thing, like this. And maybe the constant gets doubled, we don't care. Okay. And then you can see how this is going to play out, right? So this thing is less than this. And then we apply Cauchy-Schwarz to the mixed term. Cool. And now we're in good shape. Let's erase some space. Put it here. So we do the standard thing at this point. So take v of h of x, which is defined to be u of x plus h times whatever direction ej minus u of x over h. This still satisfies this differential inclusion because we have a linear subspace. We can apply this estimate we have here, so then let's call this thing star star. We have that integral of, let me change pens. It's not much better. It's definitely not better. Okay, And since we know that W belongs to W12, this thing is going to be a nicely bounded sequence in L2, right? So this is bounded in L2, this is bounded in L2, it's uniformly bounded for all small h. Yeah? So the only way that this inequality is true for all small h, and of course there's a constant c here, is if this thing is indeed bounded for all small h2, right? Because these are basically bounded by, or these are actually bounded by fixed constants for all small h. And if this guy was unbounded as h got smaller and smaller and smaller, we'd have a contradiction because we're bounding this by a constant plus a constant times the square root of it, right? So for all small enough h, this integral here has to be uniformly bounded. Yeah, there's a little algebraic exercise to actually find the bound, but I hope it's kind of clear just from this inequality. So this implies that integral of dvh squared rho squared dx less than some particular constant, say c1, for all small h, i.e. we now have the ability to get another derivative out of our function u, right? So this differential quotient is bound for all small h, again, by this theorem we learned in the elliptic regularity warm-up. This gives us that we actually have that the jth derivative of the derivative exists. So let's write it like this. So jth derivative belongs to W12. J is arbitrary, so this implies that I want to write consistent things for any j, which implies that u actually gains another derivative, W22. And then we can iterate, because we do have a subspace. So then we can set up this machine again, and we can take this difference quotient of whatever order of derivative we want, and just repeat, and we'll have that all orders of derivative exist. Yeah? And then, as we've seen before, by solve embedding theorem, we'll actually have that we'll hold the continuity of any order of derivative we like, and therefore the thing is C infinity. So just repeat. And by holder, also by solve of embedding. U is C infinity, which completes the proof, right? So what we've learned is that if we have a differential inclusion into a subspace without rank-1 connections, just that fact alone gives us that U is C infinity. And the special case we saw right at the beginning of the course of K being the two-dimensional conformal matrices is just a special case. Okay.